Good day everyone. Let's discuss about analysis of algorithms. Algorithms require time and memory space to execute. These factors are commonly based on the size of the input or the quantity of data entered into the algorithm. For this session, we'll focus on time complexity or running time more than running space. Now you might think that the following factors should also be considered. However, we will limit our analysis to be independent of technological factors. These factors tend to differ depending on the time period. Computers 10 years ago are much slower than what we have today. Instead, we will only depend on the fundamental factor of size of data or input. Thus, our analysis is not an accurate measurement of time. Rather, it's an estimate to compare different algorithms of the same task and to predict performance. For example, consider the task of getting the sum of the numbers from 1 to n. We have two ways to solve this, by getting the summation of I from 1 to n or using the shortcut quantity of n plus 1 times n all over 2. For the summation, the number of times we use addition is dependent on n, meaning if n is 10, we add 9 times. If n is 100, we add 99 times. For the second solution, we only perform one addition, one multiplication, and one division regardless on the value of n. From this, we can say that the second solution is faster for higher values of n. Later, we'll discuss which values of n we'll consider for our analysis. Now we have the following assumptions for our analysis. First, we assume that our algorithm will run on single processor machines, meaning all instructions are executed one after the other. No two operations may execute at the same time. Secondly, we assume that our machine has random access memory, meaning all data access have the same speed. Let's talk about cost. Cost is the amount of time an instruction requires to execute. We can assume that the same instructions have the same costs, and different instructions have different costs, but they're all constant. For example, we can assume that the assignment operation has a running time of C1, and the multiplication operation has a running time of C2. C1 and C2 may or may not be the same, but we know that they're constant, such that repeating the multiplication operation x times has a cost of x times C2. With all those assumptions and details, we now define the running time or time complexity of an algorithm as the total sum of the cost of all operations relative to the size of the input. The running time is indicated by T of n. Let's look at this example. Here's a simple linked list node called variable. The root of the linked list is defined globally, and the function to get an element of the list based on the character parameter. We can assume that the linked list already has n elements previously entered. Let's review how this function works. It starts by having a temporary pointer at the root. It then checks if the pointer does point to something and if its property var is not equivalent to the parameter. If so, we move on to the next element of the list and do the same check. At the end, whether we find it or not, we return the value of t. Let's derive the t of n of the function variable find. Line 10 is always executed once. Thus, we put C10 in the equation. The subscript indicates the line number. Line 11 is executed a variable number of times depending on the size of the linked list and if this condition is satisfied or not. For now, let's leave it as C11 times I. It can be argued that line 11 consists of multiple operations such as checking if the condition is true, checking if t is null, the logical AND operator, the arrow operator, and the not equal comparison operator. However, all these are encompassed by the operation of checking whether the whole condition is true or not. Thus, we only consider it as a single instruction. Line 12 is executed one less than the condition because if the condition becomes false, the statements inside the loop no longer execute. Thus, we put it in the equation as C12 times the quantity of I minus 1. Line 13 does nothing, just indicating the end of a loop. And line 14 is executed once, hence we add C14 in the equation. Looking at our equation, we have a variable I which depends whether the condition in line 11 is satisfied or not. To analyze this, we need to discuss the different possible scenarios for the algorithm. I'll point out 3 possible scenarios or cases. Our best case would be when the node that we're looking for is in front of the list. In this case, the loop only checks once and the condition becomes false immediately, ending the function, making I equal to 1. Notice that in this scenario, line 12 does not execute. Now the worst case would be when the element that we're looking for is not in the list. In such a case, the temporary pointer will reach the end of the list only to find out that the target element is not there, making I equal to the size of the list, or n. However, most of the time, the target element would be somewhere in the middle, making I a range between 1 and n. Let's give these cases proper notations. The O notation indicates the maximum running time or worst case scenario of an algorithm. The omega notation indicates the minimum running time or best case scenario of an algorithm. The theta notation indicates the range of running times of the average case. Going back to our example, we substitute the values of I depending on the case that we're looking at. For the best case, I is equal to 1, reducing the T of n to this. For the worst case, I is equal to n, making T of n like so. Now the average case is actually anything in between these two. Of these 3 notations, we consider the O notation as the most important because we gain deeper insight when an algorithm behaves at its worst, just like humans. Also, the worst is the worst. Nothing could be worse than the worst. The O notation can also be referred as the O of n. To get the O of n, given the T of n, we will only consider the largest growing part of the function, meaning the O of n of the algorithm is the limit of T of n as n approaches infinity. Let's plot a few possible O's of n in Excel. Let's have a linear function, a logarithmic function, n log n, quadratic, cubic, and exponential. As you can see, the exponential dominates the graph. Everything else is negligible compared to the exponential series. Let's remove this to see the others. Removing the exponential part reveals the second fastest growing function, which is cubic. Removing the cubic part reveals the third fastest, which is the quadratic. Removing the quadratic part reveals that n log n and the linear functions. You can also see here that the n log n has lower values compared to linear when n is less than 10. But since we're taking the limit as n approaches infinity, this does not concern us. And lastly, the slowest growing part of a function is log n. This graph is actually quite similar to the square root function. Let's look at more examples. Given the following t's of n, get the o's of n. Let's have different values of n for the first example. When n is equal to 10, n squared is 100, 3n is 30, and 100 is 100. The total would be 230. As you can see, the contribution of the constant 100 is nearly 50% of the total running time, same as the n squared part. Increasing n to 1000, n squared becomes 1 million, 3n is 3000, and 100 is 100. As you can see, The 3n and 100 contributes less than 1% of the total running time, making them negligible. Thus, we can conclude that the O of n of the first example is n squared, or quadratic. Inspecting the second equation, we can instantly deduce that the O of n is 2 raised to n, or exponential, since it is the fastest growing part of the function. Here's a list of common complexities ranging from fastest to slowest. All of them are relative to n, except for the first. Constant running time means the algorithm has the same cost regardless of the size of the input. Let's add some technological factors to see their differences. Let's assume that we have a computer that can constantly execute one step per nanosecond. In the first three complexities, notice that the execution time is always less than a second, even if we increase n from 1000 to 1 million. Looking at the quadratic, the execution time becomes noticeable for n greater than 10,000. For the cubic, even when it's just 1000, execution time is already noticeable. As for the exponential, well, honestly, I don't think anyone is willing to wait for centuries for their algorithm to finish. Let's change the computer from 1 GHz to 10 GHz. Considering the quadratic function with n at 10 and 100,000, we can estimate that the 10 GHz computer would run at a tenth of the speed of the 1 GHz computer, giving us the following execution times. Notice that increasing n by 10 times and increasing the speed of the computer 10 times will still yield a 100-time difference because 1.667 minutes is the same as 100 seconds. What am I trying to say? A computer's limitation is not the processing power of the CPU. Rather, it's the complexity of the algorithm. As programmers, it is our objective to optimize our algorithms rather than rely on the CPU speed to reduce execution time. I hope you learned much from this and clearly understood how algorithms are analyzed. If you have concerns regarding this video, you may contact me by sending an email to inquiry@ceratol.com.